This instructional video will demonstrate how to solve acid-base equilibria for a polyprotic acid. This simply means that we will have multiple dissociations, in this case 2, and we have H2S, we have its concentration, and we have equilibrium constants for the first and second dissociation. So the first dissociation can be written out, showing that we will remove one hydrogen and we'll have the HS minus ion. The second dissociation looks at what happens when the second hydrogen comes off. So we'll have this one to solve. In both cases we're going to use an ICE table, I for the initial concentrations, C for the change in concentrations, and E for the concentrations at equilibrium. So, initial, change, and equilibrium. We have that we start out at 0.10 molar. We have no ions to begin with. Everything is 1 to 1, so our change is minus X on the reactant and plus X on both products. So finally at equilibrium we add up these two to get the amounts that we have. Now, for this one, since this is the first dissociation, we'll use the first Ka, Ka1. So that's 1 times 10 to the minus 7 equals the hydrogen ion concentration times the HS minus ion concentration divided by the concentration of our undissociated hydrogen sulfide. Now we can use the approximation method to find a value here, and then test to make sure that what we find is less than 5% of this initial amount. So this gives us that 1 times 10 to the minus 7 equals x squared over 10 to the minus 1. This means that x squared is equal to 1 times 10 to the minus 8. So taking the square root of both sides gives us a value of x of 1 times 10 to the minus 4. And the question then becomes, is 1 times 10 to the minus 4 less than 5% of 10 to the minus 1? And this does in fact pass the 5% test. So, very happy about that because it allows us to take a value for x. Since we can neglect it safely, we now know the concentration, H2S. And now that we have this value for x, we have the amount of hydrogen that will be a common ion here, and the amount of HS minus that we're going to have to worry about dissociating. And so we have 1 times 10 to the negative 4. We have 1 times 10 to the negative 4, and we have nothing here. That's our initial. Our change, same as before, minus x, and plus x. And then our equilibrium amount is 1 times 10 to the minus 4 minus x. Here we have 1 times 10 to the minus 4 plus x, and here we just have x. So because we have our concentrations in the ICE table, it's straightforward to write out the expression, this time using Ka2, 1.3 times 10 to the minus 13 equals the hydrogen concentration, reading that directly from the table, times our sulfide ion concentration, all divided by HS minus. And so now it gets a little more challenging to worry about all of the tips and tricks with approximations. So we can just do this using the quadratic formula. So I'll multiply through here, getting 1.3 times 10 to the minus 17 minus 1.3 times 10 to the minus 13 x, and this is going to equal 1 times 10 to the minus 4x plus x squared. So we can rewrite this as a proper quadratic, and we have that 0 equals x squared plus 1 times 10 to the minus 4x. When we combine these two values, 1.3 times 10 to the minus 13 is extremely small by comparison to 1 times 10 to the negative 4. So our coefficient just remains 1 times 10 to the negative 4. And then our constant term, 1.3 times 10 to the minus 17. So we have a equals 1, b equals 1 times 10 to the minus 4, and c equals minus 1.3 times 10 to the negative 17. And so now if we use the quadratic formula, we find a value for x as 1.3 times 10 to the negative 13. And so this value of x then is what we will use for our sulfide ion concentration. And we find that we can simply copy over the value 1 times 10 to the negative 4 for our hydrogen ion, because x is so small relative to it, and 1 times 10 to the minus 4 for HS minus. So sulfide is equal to x. The hydrogen ion concentration and the HS minus. So by using stepwise dissociation, it's possible to find equilibrium values for all of the species found in both of these steps.